Get my screen shared. Oh, you weren't supposed to see my messy desktop. Okay, hopefully that's showing up all right for everybody.
Looks good.
Thank you. All right. Okay, so thanks for the introduction. Thanks to DREGS for having me here today. And thanks to everyone who's participating. I know we all must be sort of on the same edge of complete virtual exhaustion. So thanks for showing up for one more Zoom talk. I'm going to try to talk about 3 different forms of alteration that I've sort of stumbled across in the deep root zones of porphyry copper deposits. I have probably tried to fit way too much into this talk, so I will be speaking quickly. So luckily we have a questions portion at the end. This is work that I started during my PhD at the University of Arizona, and I've sort of continued on different facets up until now, continuing still on some of these projects. And so as a result, there are many different collaborators, companies, societies that I have to thank for their contributions to the understanding, to the studies, for access to sites and samples, and for support, funding support that helped sort of guide a lot of this research. So just diving right in, why study the root zones of these porphyry systems? And really, a lot of my interest has come from this fact that, if we look at this beautiful figure here that I've swiped from Silito 2010, we have such a wonderful understanding of the cores and the tops of these porphyry systems, these porphyry copper systems. If you look at sort of the area in red here, we have all of these different types of veins. We're not even worrying at this point about all the different forms of hydrothermal alteration that we know comes along with the cores and the tops of the porphyry systems. Depending on the system, preservation and exposure, we may even get into some, highly advanced argillic, maybe high sulfidation sort of low to epithermal settings. But then when we look at sort of the bottom third of this image, we go from all of this understanding, all of these different forms of alteration and mineralization to somewhere at depth, fresh stock and porphyry. And until recently, I think a lot of this sort of transition zone from this really intense alteration and zonation of our mineralization in the cores of these porphyry systems down into depth really hasn't been looked at. And so that's sort of what captured my interest. And so really trying to better understand what does it look like under the cores of these systems? When do we actually transition into fresh or ostensibly unaltered porphyry and stock? And what do these different forms of alteration look like? How do they vary from system to system? And how do these forms of alteration contribute to our understanding of porphyry copper deposits more as really extensive geochemical systems, as opposed to just where the mineralization is and where the mineralization isn't? So I'm sure most folks here are pretty familiar with porphyry systems or porphyry copper systems, but just to sort of jog the memories of those who may be focused on other deposit types for a while. Of course, there's a range in different porphyry deposits that are typically classified by the main metal byproduct, associated magmatic composition, but all of them, whether they're tin, tungsten, porphyry, moly, gold, copper, are essentially related to a hydrous magma body that's typically fairly shallowly emplaced into the crust. Because there are a range of different magmas that can produce these porphyry systems, we tend to see then a slightly different composition of the hydrothermal fluids that they exsolve. And these form, of course, different types of mineralization, but also slightly different forms of hydrothermal alteration. When it comes to the porphyry copper system specifically, we're typically dealing with shallowly emplaced sort of intermediate magma bodies. So though we see a range and of course natural examples, commonly spanning sort of granodioritic, tonalitic, into the quartz montanitic and granitic fields. And the mineralization, alteration itself tend to be most strongly tied to late stage porphyritic or porphyry bodies with high water content. And of course, when these late stage bodies are actually crystallizing and cooling, then they exsolve off this separate magmatic hydrothermal aqueous phase that then carries all of the elements we're interested in, all the goodies like copper and moly, but also of course things like potassium and chlorine and sulfur that then will interact with the surrounding host rock, make our different forms of hydrothermal alteration and inevitably deposit our mineralization as well. We know from a lot of fabulous work that's been done by so many wonderful economic geologists in the past that the alteration in the cores of these porphyry systems form very commonly very nice alteration zoning. So the model put forth by Lowell and Gilbert in 1970 with our sort of high temperature potassic core, where we're typically seeing most of our copper mineralization, then zoning up and out into a more hydrolytic form of alteration, sericitic, commonly referred to as phyllic. In many systems, developing sort of argillic to advanced argillic as well. And then of course, shallowest and most distal are propylitic form of alteration. And this is really where the vast majority of work has been done on these porphyry systems. And of course, this makes sense because this is where the mineralization also is. In 2008, Seedorf et al. Put out a paper in economic geology where this figure comes from, and you will be seeing this figure a lot through the talk. And basically what this sort of showed was, how do we extend this porphyry model to depth? What other forms of alteration are present beneath the ore zone that can tell us a little bit more about how these systems are forming, or if we're in a highly dismembered region like Basin and Range Province, maybe it can even tell us if we're in the root zone of a dismembered, chopped up porphyry system. And so the addition of sort of this sodic calcic family of alteration in the blues and purples on the left here, and coarse muscovite alteration on the right were sort of two of the big takeaways of what are deep forms of alteration beneath porphyry systems. I should make a quick aside that in the 2008 paper, this coarse muscovite alteration is referred to as Greisen. I have since sort of deviated from that terminology because it tends to upset a lot of folks who've worked in true tin tungsten lode systems. So just be aware if you end up going back to that paper, what I'm talking about is coarse muscovite, used to be referred to as Greisen. And the systems I'm going to be talking about really can be sort of shown here on this map on the left. The vast majority of systems I've worked on are laramide porphyry copper systems across Arizona, so in this sort of red swath here. But I'll also be mentioning some work that I did in the Yerington district in Western Nevada, which of course is associated with the Jurassic arc. And all of these locations are basically perfect for the documentation of these deep forms of hydrothermal alteration because we have the overprint of younger extension. So we've had so many sort of episodes of cutting and offsetting normal faults that we've been able to expose these relatively deep forms of alteration at surface. Okay, so the first form of alteration, coarse muscovite. I'm going to make a quick aside here as well before we get into this. At this time, the way that I define coarse muscovite alteration is mostly based off of a given mineral assemblage. So it's this coarse muscovite, quartz, we'll get into the other associated hydrothermal minerals. And this form of alteration has had varying recognition as well as sort of different names, depending on which system you're working in. So as I sort of mentioned, coarse hydrothermal muscovite with quartz and a bunch of other various sort of accessory minerals, things like tourmaline and topaz would be referred to as Greisen in a tin tungsten system. Coarse hydrothermal muscovite with quartz, plus or minus fluorite, plus or minus molybdenite, might be referred to as Greisen in a quartz montanitic granitic moly copper system. But it really wasn't until this 2008 paper that this sort of coarse muscovite, or as it was called, Greisen alteration, was reported from sort of more granodioritic, tonalitic, porphyry copper systems in Arizona. And what really fascinated me about this coarse muscovite or Greisen alteration was that it had been reported from a handful of systems, but it was really, lacking, or it hadn't been observed in very well-known, very well-exposed porphyry copper systems. And what ended up happening was I happened to be doing some contract work out in Yerington mapping the Lure Hill area. So for those of you who are familiar with Yerington, these exposed rocks on the left here represent the Singatsi Range, Yerington Mine here, Pumpkin Hollow property down to the southeast, So the town of Yerington would sit sort of out in this young cover. And everything today I'm going to be talking about from the Yerington district is actually from the mapping that I did in the Lura Hill area. And I was out there mapping what I expected to see, a lot of sodic-calcic alteration. And it was when I came across the coarse muscovite at Lura Hill that something sort of clicked and said, you know, we know that this is in a handful of places. It's here in Yerington, which is such a, you know, an archetypal porphyry system. It hadn't been sort of the focus of previous workers' studies out there before. Maybe this is something that's really out in a bunch of different systems, and people just really haven't focused on it because it's so far removed from typically the mineralized centers of these porphyry systems. So I've done some work on the coarse muscovite alteration out at Lura Hill, and then I decided to take that back to Arizona and go to a handful of laramide porphyry copper systems and try to sort of look for it in a bunch of systems and better document, you know, what are the mineral assemblages, what's the variation, what's the timing of this form of alteration. So we're gonna run through basically sort of the big takeaways and highlights of what I've found so far. And some of these things I think I'm very confident in, and other things I hope more workers come in and start to add more observations so we can be sort of more confident and test some still outstanding hypotheses. When it comes to this coarse muscovite alteration, it tends to be deep and proximal in a given porphyry system. So when I say deep, there's a little bit of wiggle room here because in most of these systems, I'm basing this estimate of paleodepth, original paleodepth, off of structural reconstructions. Where possible, where we have geobarometry and thermobarometry, we can use that to constrain, but there's a little bit of wiggle room on these estimates. But in some of the shallowest examples, I think we're probably around 3 kilometers paleodepth, and this probably spans in certain systems down to maybe 10 or 12 kilometers paleodepth. It's also extremely proximal, and so what I mean by that is we tend to see this directly beneath a mineralized cupola. And so for the majority of samples of the coarse muscovite veins and alteration, they tend to be hosted within the porphyry body itself or just underneath that stock. And we can see examples of where these veins and alteration have gone out into host rock, sort of country rock, but it tends to be really only where it's directly adjacent to the plutonic contact itself. So this is one example of a coarse muscovite vein cutting out into some Proterozoic host rock, but again, right along the contact of the laramide intrusion. When it comes to the actual spatial extent, you know, trying to estimate volumes of this form of coarse muscovite veining and alteration, we find that it's really variable between systems. So this is, oh, my little circle got shifted here. This is the Lura Hill area, again, out of the Yerington District, Nevada. The geology, of course, from the Prophet and Dillis 84 map, and then my alteration mapping sort of overprinted on that. There's a tiny, tiny little brown blob on this sort of eastern side of the Lura Hill area here. And that is the only area in which you can see pervasive wall rock alteration with this coarse muscovite alteration. There are veins that extend to the north and south of there, but really it's sort of limited to maybe 100 square meter exposure. In some of the systems in Arizona, including the sort of Gunnison, Sierrita, and Globe Miami areas, you have significantly more extensive sort of surface area where this veining and alteration is exposed. As a sort of quick disclaimer there, when I say greater than 6 kilometers, greater than 10 kilometers squared, those areas are not entirely pervasively replaced with coarse muscovite, but these are areas where there's sort of consistent 1 to 3 veins per meter coarse muscovite veining, plus or minus some localized wall rock alteration. So when we think about these really variable spatial extents, we always have to sort of keep in mind the only reason we can even see this is because we've gone through so many different stages of extension. So the volumes or the surface area that we're seeing is strongly controlled by preservation and exposure. That said, I think it's very likely that even if we were to get sort of 3D control and be able to better estimate the volumes of this alteration, there's probably a pretty big difference from system to system. In terms of what this actually looks like, so coarse muscovite alteration and veining, the veining is far more common, but every system that I visited where this coarse muscovite alteration is developed, we saw examples of this pervasive wall rock alteration. So this is a map from Cooper and Silver 64. This is the Gunnison deposit. Some of you might know this as the I-10 deposit in Arizona, because I-10 is literally sort of running through the center of the stock here. For others, may be familiar with the Johnson Camp deposit. That's actually just north off the end of this map here. So it's got a lot of names. It's a very cool system. All of this light blue here is the Texas Canyon quartz monzonite. And all of these slightly darker swaths, which hopefully you can see, are mapped as Texas Canyon quartz monzonite altered. And so on the images on the right here sort of show you what that means. So on the top is the Texas Canyon quartz monzonite. Fresh, in a lot of these systems, you sort of get as unaltered as you can, but we can at least see sort of disseminated black biotite booklets. You have this nice sort of pink K-feldspar phenocryst here. And then the bottom image is from one of these darker swaths, the altered quartz monzonite. And hopefully you can see that there are these really nice euhedral disseminated booklets of muscovite throughout the rock. And I know they look a little bit dark, it's because they're thick and, you know, within the host rock, but these are all muscovite booklets. And another neat thing about this pervasive alteration is that this rock gets up to sort of 4 volume% disseminated fluorite as well. And we can see there's no stable biotite left. The vast majority of the feldspars have been replaced. And so, you know, someone who hadn't seen an image of this fresh stock on top might come across a rock like this and, oh, this is, you know, potentially a 2 mica granite to start off with, but really, really pervasive wall rock alteration. And we found pervasive wall rock alteration in every district. It tends to be significantly less voluminous than in this Gunnison deposit, but definitely present. Significantly more spatially extensive are coarse muscovite veins. One of the things that kind of surprised me about the veins is that they very commonly have open space textures. So hopefully you can see that in these 2 images on the left here, where we have these euhedral sort of terminated quartz crystals, pyrite and muscovite. The image on the bottom here, these are terminated albite and K-feldspar crystals. And they also span from sort of more wavy walled or almost ductile looking to planar in morphology. When we look at sort of the alteration that's taking place in the vein halos as well as the wall rock replacement, we typically see sort of this trend of any original K-feldspar gets replaced by a mixture of muscovite, a little bit of K-feldspar, and then a little bit of albite. Original plagioclase goes to a mixture of muscovite, albite, and K-feldspar. And the mafic minerals tend to be the least stable. They tend to be completely altered first. And they're replaced by a mixture of muscovite, hematite, rutile, and pyrite. And I should mention, when I say albite here, I'm talking about an anthracite component of 0 to 6, so extremely sodic in composition. All veins and alteration across all the districts that I observed this form of alteration in contain sort of 5 main minerals, the muscovite, quartz, pyrite, K-feldspar, and albite. And then the mineralogy became much more variable between districts. And so what we would typically see is in a handful of systems, these veins and alteration could be accompanied by pretty substantial chalcopyrite, molybdenite, and fluorite. And then we could sometimes find trace scheelite and wolframite. And when we stepped back after sort of collecting all of this information, we found that there tended to be a nice association between the mineralogy that we found in these coarse muscovite veins and the associated magmatic composition. And so when we had these coarse muscovite veins that had chalcopyrite, molybdenite, and fluorite in fairly substantial amounts, these tended to be associated with more granitic to quartz monzonitic compositions. Whereas when we were dealing with systems that were more sort of tonalitic to granodioritic, we didn't have that good amount of chalcopyrite, moly, or fluorite. We tended to have the more sort of run-of-the-mill muscovite quartz pyrite compositions. You could get sniffs of chalcopyrite in these veins when we're in the granodioritic to tonalitic systems, but never, flashy veins like this example on the left here. Along with the mineralogy being variable between districts, one of I think the most fun things about mapping these veins out is that they tend to change mineralogy and morphology along strike within a given district. So on the left here, this is an example from the Granite Mountain area, which is the roots of the Ray porphyry copper system in Arizona. And there are these really, really massive veins that are exposed at surface here. And we could follow them from an interpreted paleo sort of deeper to paleo shallower. Again, you have to sort of buy into the structural reconstructions here to accept these interpretations. But we found the same sort of systematic change in mineralogy and morphology along strike over, I think, maybe 10 big veins at surface, where we would start off in the deepest areas, the deepest exposures, with these sort of wavy walled quartz plus or minus Cape feldspar veins. And as you would follow these to paleo shallower, it would be a whole bunch of these sort of wavy walled, maybe 1 to 6 centimeter wide veins that would coalesce into one large quartz occurrence, sort of shown here. But within that quartz, you could see all of these more individual, sort of smaller sheeted quartz veins that had coalesced together. And this is where we'd start to pick up small sort of trace amounts of the coarse muscovite. But as you followed this even shallower in the system, these veins would blow out such that the center line, sort of maybe a ½ meter to a meter wide, would become sort of milky bull quartz. And then on the side, you would get 1 to 2 meter wide envelopes of this pervasive muscovite wall rock replacement. And we saw this trend sort of over and over again in this area, in the roots of Ray. As sort of a comparison, this image on the right here is sort of a schematic of the mineralogy and morphology changes in coarse muscovite veins from the Lur Hill area. And so what was kind of neat there is, as I mentioned earlier, there's a very small area at surface where we actually have pervasive wall rock alteration with coarse muscovite. And in those areas of pervasive wall rock alteration, the veins were wavy walled. They had thick center lines with the terminated quartz, pyrite, and muscovite, and you could follow those along strike. And as you walked out of the pervasive wall rock alteration, they would become planar, they would lose their center lines, and they would become muscovite only veinlets. And eventually, if you followed them far enough away and these things had broken off and been exposed to weathering, they would just look like chlorite fracture surfaces until you sort of walked them back into these much thicker, much more wavy walled features closer to the pervasive wall rock alteration. I wouldn't say that we necessarily saw similar trends in this sort of variable morphology and mineralogy between districts, other than to say it's really characteristic of these veins to pinch and swell drastically over just a couple meters. And in case you didn't pick it up from my last slide, we think that coarse muscovite veins probably restore to having originally being emplaced either subvertically or sort of subhorizontally, depending on which system you're in. This map on the left here, please ignore my gaudy colors. Each one of these strikes and dips is a different coarse muscovite vein. The colors just represent, did this have a K-feldspar envelope? How thick was this? Was it wavy walled or not? But I think it's fairly fair to say that there's a really strong orientation in these veins, that they're all sort of pointing up to the top left of this image here, and basically they're all pointing towards the Miami mine. And so these are all in sort of what's considered the root zone. They're not themselves mineralized, But if you believe some of the structural reconstructions that have come out of here, these would essentially be pointing vertically when they were originally emplaced. On the right is a map of the coarse muscovite veins from the Lure Hill area in Yarrington. Here we've oriented such that north is to the right, and so the interpreted sort of restoration of the Bear deposit would be sort of up to the top off this map. And here you can see the rough orientation would restore to basically sub-horizontal. We think this is probably a reflection of whether or not these veins are being emplaced under hydrostatic or lithostatic conditions. And in one system, actually the Gunnison system, where I showed the two images of the Texas Canyon quartz monzonite and then the pervasive alteration, there we were actually able to map out in the deepest portions of the system, everything was sort of sub-horizontal, and as you got closer and closer to the top of the system, shallower in the porphyry system, you're able to see these veins sort of roll over to sub-vertical orientations. In terms of better understanding the timing, it's a little tricky with the coarse muscovite because it is typically so deep in the system. Where we do have good overlaps with other forms of hydrothermal alteration, it's usually with potassic or sodic calcic alteration. I have yet to see any examples where coarse muscovite overlaps with propylitic or cericitic or any other sort of hydrolytic form of alteration. What we can say where we do have good cross-cutting relations is that typically the coarse muscovite postdates sort of the bottom of the potassic alteration zone. So there's an image here on the left where we have a nice a sulfide pore quartz K-feldspar vein that has been cut and offset by a later coarse muscovite and quartz vein. And this is a pattern that we've seen in a handful of districts. When it comes to the timing relationships with sodic calcic, it gets a little bit more complicated. There are a handful of districts in which it really seems like the coarse muscovite predates the sodic calcic alteration, but in other systems it's really hard to tell, and there almost seem to be sort of reverse timing relations. So this is one of the areas where I would really appreciate if other folks want to go map some deep root zones of porphyry systems to add more data to this understanding. But in general, we do think, at least with sort of timing relations to mineralization within a given porphyry system, the coarse muscovite is likely late and likely postdates mineralization. And so with sort of all of the observations we're able to make across a wide variety of different porphyries, our current sort of interpretation, or at least my current interpretation, I won't drag my co-authors into this, is that coarse muscovite forming fluids are likely magmatic hydrothermal. And I believe that they are likely exsolving off of these magmas sort of late in the crystallization. Why I think they're probably magmatic hydrothermal, the potassium dominant cation load is what we would expect for these compositions of magmas. The fact that in terms of sort of spatial relations, these are proximal to and mainly hosted within the stocks themselves. And the fact that we're able to tie the variable mineralogy of these different veins and alteration to the magma compositions, where we see much more variable alteration assemblages associated with the granitic to quartz monzonitic compositions, and the more sort of banal, you know, muscovite, quartz, pyrite compositions associated with the more granodioritic to tonalitic suites. So I say it's late. What does that mean in sort of the context of these, you know, complex porphyry systems? I think there's really two main possibilities. We're either looking at a late fluid that's coming off of a mineralizing pluton after it's formed, porphyry mineralization, or we're potentially looking at sort of a passive degassing of an underlying batholith. And, you know, the only way to really get at this, I think, is looking at sort of the time-space relations between the coarse muscovite veins and given mineralizing stocks. This map on the right here is just vein densities of coarse muscovite alteration from the Miami, well, the Globe Miami district, and you can see sort of the outline of where the Miami Inspiration mine workings are here. So we're mainly working a little bit to the west. And from mapping out the vein densities here, sort of two things became apparent. One thing is that there's sort of a core area where we have the highest vein densities, and they become pretty intense in terms of the density. And this is also where we have sort of localized wall rock replacement. And to me, this is potentially sort of a localization that may represent late fluids coming off of a mineralizing pluton. However, if you've ever been basically anywhere west of the Miami workings out in the Schultz granite in the Globe Miami district, you'll know that there's basically 1 to 3 meter, fracture coatings of 1 to 3 every meter, sort of basically anywhere out here. I mean, you can drive along Highway 60 and it will flash sort of glittery muscovite at you anywhere along these outcrops of the Schultz. And so in this case, this is something that I think the vein densities may actually indicate both sort of high densities of coarse muscovite coming from the late fluids from a mineralizing pluton, and then these sort of highly disseminated, really, really extensive fracture coatings could potentially be related then to passive degassing of an underlying batholith. But this is something that I would say I'm still, you might notice that there's 3 question marks on this slide. I'm still open to sort of hearing more thoughts, and this is something I think would really benefit from, you know, detailed vein mapping in a variety of districts. So from all of those observations across a variety of different districts, something that really jumped out and sort of where I stand with this now is that there were sort of 2 distinct classes of coarse muscovite veins in alteration. And those that were associated with granodioritic to tonalitic porphyry copper systems tend to occur below the ore shell. The very shallowest exposures are typically overlapping with the very bottom of the potassic alteration zone. They postdate mineralization and are themselves very poorly mineralized. And then the other group that tends to be more associated with the quartz monzonitic to granitic magmatic compositions are very well mineralized, sometimes actually composing some of the ore zones themselves. And these are the ones that contain sort of the wider variety of minerals, the sort of as implied by being mineralized, the molybdenite and chalcopyrite, but also the fluorite and the trace scheelite and wolframite. And so this is something that I think is really fascinating because, you know, if you happen to be out exploring green fields and you find a whole lot of coarse muscovite alteration that's really, really well you know, endowed with molybdenite and fluorite, that might tell you a little bit more about what sort of porphyry system you're exploring. All right, alteration style number 2. So we're going to flip to the left side of this, this figure now and talk very briefly about the sodic calcic sort of family of alteration. I got really interested in this again because I had sort of started by working, you know, my master's was in the Yerington district, and so I had been exposed to beautiful, extraordinarily strong sodic calcic alteration that had been really well documented by previous geologists before. And then I started working in these laramide porphyry systems, and it's just not, you know, recognized very much. It's not talked about as much in the laramide porphyry systems in Arizona. So the goal is to go out and just map, you know, look for it, characterize it, and do sort of a brief compare contrast with the sodic calcic alteration in the laramide arc versus at least what we see in the Yerington district. From going to maybe 7 or 8 different districts in Arizona, really came across basically 3 main sodic calcic assemblages. The albite epidote alteration assemblage is by far and away the most common. It is albite epidote chlorite typically. And one of the neat things about this albite epidote assemblage is that in certain districts, it would be extensive over a really, really wide vertical section. Again, structural reconstructions and interpretations there to estimate this, but in certain systems spanning from sort of 3 to 8 kilometers paleo depth. This alteration could form proximal or distal to a porphyry system. Lots of times you would see it out in host rocks as opposed to in the porphyry or the laramide intrusions themselves. The second form of sodic-calcic assemblage that we would commonly come across was this plagioclase epidote actinolite. And so here the plagioclase typically was a little bit more calcic in nature, and we were replacing sort of the chlorite-dominated assemblages with now a calcic amphibole. When we had districts where both the albite epidote and the plage epidote actinolite assemblage is present, this actinolite-bearing assemblage tended to be deeper relative to the albite epidote. And the third calcic assemblage is this pure or garnet form of alteration that we would see. Garnets, oligoclase, actinolite, plus or minus epidote. And this was really, really locally developed. We typically wouldn't see outcrops more than, maybe a couple tens of square meters at surface. And this tended to be very deep. So in the handful, the rare systems where we get to see all three assemblages exposed at surface, this would be the deepest sort of form of sodic-calcic alteration. One of the things I run across a lot when I talk about the albite epidote chlorite assemblage is, well, this is just propylitic, this is just deuteric, is this really truly, some sodic calcic alteration? And so we did go ahead and do a fair amount of whole rock analyses, looking at, can we actually characterize mass balance changes? Here, what we did is we have the fresh and altered pair of each. So, for the Calvin Riverside calcic assemblage, we had this sodic calcic alteration. We had the unaltered rock that it was hosted in. We got whole rock analyses of each. We used the Gresson's isocon method to try to pick out an apparently, anyway, fluid immobile element to normalize that too, to try to actually say, did we add or remove elements to this rock, or did we just change the minerals around? And so what we found was for all of these different forms of sodic calcic alteration, we truly do have an addition of sodium and or calcium, and typically then a paired loss of potassium. Something to keep in mind that I thought was really cool is that the changes in iron, magnesium, and manganese are sort of all over the place. And part of that, I think, is strongly influenced by the temperature, pressure, and protolith compositions, such that, these big peaks in manganese from the Kelvin Riverside assemblages happen to be in areas where the temperatures and pressures were high enough that we were forming garnets, and the garnets took up a fair amount of manganese in those hydrothermal minerals. Sort of one other thing that really jumped out about the sodic calcic alteration in the laramide systems was that there's often multiple episodes of sodic calcic alteration in a given district. And so we would have, sodic calcic alteration that showed good spatial association with these laramide plutons, where we interpret that, likely external fluids are being circulated by the thermal input of those intrusions. Those showed a broader range in composition, from those albite epidote through plagioclase actinolite to the diopside or garnet bearing assemblages. And they're commonly spatially associated with laramide stocks that happen to intrude Paleozoic sedimentary sections. Then we have these younger Miocene sodic calcic events, which are typically localized along extensional faults. So there's a beautiful image here. This is from Cox et al. 2006 out of the Ajo district in southwestern Arizona. And here, this extensional fault, the Gibson Arroyo, has really extraordinarily strong sodic alteration all along it. And so here there's a nice sort of spatial variant between the two. Obviously, if faults are localizing the alteration is going to really be strongly associated with those faults. And what we also found is the fault-related sodic calcic mineralization tended to really only develop the albite epidote chlorite assemblage, where we were able to observe it. A complication, of course, is that when we talk about sodic calcic alteration in the context of sort of overprinting and coming into these porphyry systems, they tend to be, or are very commonly, one of the latest stages of hydrothermal alteration. Similarly, if we're looking at a Miocene overprint, it's also going to be late. So a lot of times we don't have very good cross-cutting relationships to really narrow down the timing of the sodic-calcic alteration, other than to say post-dating the laramide, unless we happen to have good control of these sort of default control on the sodic alteration. So this just adds sort of one more complication to the joy of figuring out what's going on with the sodic-calcic alteration and the roots of these systems. When we sort of summarize what we found for the sodic-calcic alteration and the laramide, comparatively small volumes of sodic-calcic. The largest volumes and the most pervasive sodic-calcic alteration that we found overprinting these laramide porphyry copper systems are when they happen to be intruding into carbonate and or evaporite bearing Paleozoic host rocks. For a variety of reasons that I don't have time, I'm not going to bore you with, including sort of isotopic and phase relation and timing relations. These are generally then interpreted to also have formed from the circulation of a non-magmatic, sort of external, highly saline fluid source. So then how does that sort of compare and contrast with the sodic-calcic alteration from at least the Yarrington system? We see a lot of similarities, at least in terms of the mass balance changes, the mineral assemblages, the zoning patterns, as well as a handful of isotopic signatures. But when we hit on the differences, really volumetrically different. The volumes and the strength of sodic-calcic alteration in the Yarrington district dwarfs the vast majority of the laramide systems. Another difference that we found is that the laramide sodic-calcic alteration tends to have fewer examples of the calcic-rich end member. There's a lot of epidote albite chlorite floating around there. There's a fair amount of the plagioclase actinolite floating out there, but getting into those really calcic-rich garnets and pyroxene stable assemblages is pretty rare in the laramide systems. And if you buy the interpretation that this is all sort of reflective of external fluid sources, that sort of makes sense, because the Jurassic Arc in Nevada was being placed into a very arid environment. There's extensive evaporites around that could potentially be the source of these saline fluids. Whereas in comparison, the Laramide Arc was a significantly wetter climate, and a lot of these districts don't have preserved Paleozoic, either carbonate or evaporite bearing assemblages. So we've talked about these two on the left, the calcic and the sodic calcic and the coarse muscovite. Both tend to be late compared to the mineralization. They don't tend to be mineralized, but I would like to make the argument that sort of understanding these different forms of alteration, in the right geologic context gives you really important spatial and temporal clues to what's going on in an overall system. Told you I put too much in this talk. So the last thing I just really want to briefly hit on is something potentially completely different. So this is again from the Lure Hill area in the Yarrington district. And so if I want to call your attention just to this panel C here with these dark green blobs, this is a different form of hydrothermal alteration that I stumbled across, and we call this phlogopite-rich alteration. It's hosted in the Lure Hill porphyritic granite. Hopefully you can see these sort of knobby little relic megacrysts that are sticking out here in a slabbed sample. You can hopefully see a little bit of the relic texture. Basically, this is almost entirely replaced with phlogopite. All of this brown-gray ground mass is phlogopitic mica. There's a handful of sort of dravidic tourmalines spread throughout, a little bit of K feldspar. I never found one larger than maybe 500 microns, a little bit of titanite, and some fluorapatite. So this is weird, and I just have to show you these beautiful element maps to really drive home the point of this rock got completely messed up. So you can see nice euhedral K feldspar megacrysts in the top here. When you look at the magnesium element map, a smattering of sort of dispersed amphibole, and then just a complete obliteration of igneous texture. This is what I interpret to be a relict megacryst in the white here. Something that's fascinating to point out about that is it's actually a sodic feldspar at this point in its journey. But the mass balance really indicates here that we've had a loss of silicon, iron, sodium, and calcium, and basically the addition of potassium and magnesium. And I was out in this area mainly focused on sodic-calcic alteration and any form of magmatic hydrothermal alteration that might form with a porphyry system. And this just doesn't really fit anything that I was used to looking at or looking for. We were a little curious when we started thinking about this in detail if the tourmaline were actually part of the hydrothermal assemblage or if they were just in association. There were some nice little fluid inclusions hosted in the tourmaline. Here you can see a few of them are quite large, over 30 microns, that even have a nice little salt daughter crystal in them. When we looked at the tourmaline in backscattered electron imaging, you can actually see that there's two distinct episodes of tourmaline growth, this much lighter sort of euhedral point on the end, and then this darker, more homogeneous body, both of which are dravidic in composition. And the fluid inclusion data, even though we couldn't make a very good sort of estimate of what the trapping temperatures would have been because we don't know the timing, so we don't really know the depth and the pressures associated, we think these probably represent a fairly high temperature fluid. You know, before pressure correcting, we're getting temperatures of 330 degrees C for homogenization, so they trapped likely at a much higher temperature than that. And basically, the takeaway from this is the timing is completely unclear. We think it postdates probably everything around it. We think maybe that those relict, originally K feldspar megacrysts that had gone to sodic calcic or a sodic feldspar may indicate that originally this was sodic calcic alteration that has then been overprinted by yet another, this phlogopite rich form of alteration. But the fact is, we have no good constraints on timing other than it's late. It's a really bizarre form of alteration to see in these rocks. This magnesium-rich alteration when there's no ultramafic rocks that are known exposed nearby. And so all we can say at this point is we think this was sodic calcic. We think it was overprinted by a potassium and magnesium-rich fluid. We think it has nothing to do with the porphyry system. But overall, the model is incomplete. And, looking at this map and pointing out the scale bar of 250 meters, in this little postage stamp, even in the Yarrington district, there's coarse muscovite alteration, sodic calcic alteration, and this bizarre phlogopite-rich alteration. So hopefully I've convinced you that there's a lot going on underneath the mineralized core. It's complicated, and whether the alteration represents, like the coarse muscovite, late magmatic hydrothermal fluids, whether it's the sodic calcic alteration that represents, probably later, probably external fluids, or it's something completely different that you didn't expect to see and may have nothing to do with the porphyry system. Going out and keeping your eyes open and trying to understand sort of what everything is and where it fits into the context of a system will build everybody's understanding of porphyry deposits and make us better explorationists in the future. So thank you.